Hello class, these are our notes for section 2-4 for Algebra 1, equations and their solutions. So we're going to start out by talking about what it looks like to have an equation in one variable. So an equation that contains only one unknown quantity or one quantity that can be varied is called an equation in one variable. So contains, gotta have my pen here. So contains only one unknown quantity. So that would be like equations we solved in the last chapter. So if I wrote 6x minus 3 equals 9, that would be an equation with just one variable. So an equation in two variables, so if you think about one variable contains only one unknown quantity, so an equation with two variables contains two unknown quantities. And this is far more common. So this would be like taking our first equation, the 6x minus 3, but instead of having it equal to 3, we could make it equal to y. And really, we normally would have the y equals in the front, wouldn't we? So if we had y equals 6x minus 3, now we've got a linear equation. So that's going to be an equation of two variables. If we're thinking like not graphing, not that kind of math, we could think about something like 2 times your length plus 2 times your width. So that would be like a perimeter kind of thing. And then let's say it's equal to a number. Let's say it's like equal to 40. So that would be an equation with two unknown quantities. So we don't know our length, we don't know our width, but we do know our perimeter is 40. So the 40 would be like our constraint. So in order to solve it, we would have to come up with a number for L, and then we'd have to find what W would be for that L. So if I knew my length, like maybe I wanted it to be 5, then I would have 2 times 5 plus 2W equals 40, and then I would have to go through and solve for W. A solution would make it true, right? So a solution to this particular equation would be an L and a W that make this actually equal to 40. So that's another thing to look at. So we're going to go through and do kind of a longer example. I wrote example 1, but really there's only one example for this. But we're going to do a lot of different things with it. So first we're going to go through and we're going to see if we can write an equation. So we're back to math modeling. So let's read through this. Remember, when we're reading through the problem, first we're just reading it through and we're trying to visualize what's happening. Then we're kind of looking at our numbers, and then we're really trying to make sense of it and come up with some sort of equation. So suppose Tyler spends $45 on t-shirts and socks. A t-shirt costs $10 and a pair of socks costs $2.50. If T represents the number of t-shirts and P represents the number of pairs of socks that Tyler buys, write an equation we can use to represent this situation with the following equation. I don't feel like that sentence quite makes sense, but we want to write an equation for it. Okay, so let's see what's going on. So I imagine Tyler's going to the store with his mom. Maybe he already has lots of pants that fit, but he's wanting to do some school shopping, and he only needs t-shirts and socks right now. He's outgrown all of those for some reason. So we imagine Tyler can only spend $45, right? But we don't know how many t-shirts he's buying and we don't know how many socks he's buying. But he's buying some of both. Probably whatever he wants, right? Maybe he buys 3 of one and then spends the rest of the money on socks. We're really not quite sure. So let's think about how we need to write an equation, and it needs to be for our total cost. So if I'm thinking about my total cost, and I think I'm going to write a couple notes here. So my total cost is going to be equal to the money for t-shirts, right? Plus the money that we're going to spend on socks. So the way I figure out how much money I'm spending on t-shirts is I think about how I'm spending $10 for each t-shirt and I'm buying t-shirts. So that's going to be 10t. As far as socks go, I know that I'm spending $2.50 per pair of socks, and I'm buying P pairs of socks. So that's going to be plus $2.50 times P. So the cost times how many I'm buying. So that's going to be my total cost. And I know my total cost is actually going to be equal to $45. I could put the 45 over here on the left, but I know that the way we often see these equations is we have our variable part plus another variable part equal to a number. They often look like that. So it looks a little more familiar. That's called standard form for a linear equation. Linear equation because I have two variables, just like my 6x minus 3 equals y in the original, right? This would be considered a linear equation as well. So linear because we have two variables only, and there's nothing funny in there. I've just got multiplication, adding, and subtracting. I don't have any squared quantities or square roots or anything weird. Okay, so I have a linear equation, 10t plus 250p equals $45. So now they want us to go through and use that equation. This is an equation in two variables. Check to see if each pair of values for t and p make the equation true. First we want to see what happens if t is 3 and p is 6. So 10 times 3 plus 250 times 6. And then we're checking to see if it makes it true. So we're checking to see, does this really equal $45? Well, this is going to be 30. And 250 times 6 is going to be 15. So we do have 45 equals 45. And so yes, this makes the equation true. All right, now we're going to try the next one. Now we're going to try t equals 4 and p equals 2. So we're going to do the same process. We're going to try our equation. So what if I spent $10 each on 4 t-shirts? Or I guess Tyler, right? Tyler's doing this. So 10 times 4 plus, and then we're going to spend $2.50 on each pair of socks, and this time we're buying 2 pairs of socks. Is that equal to $45? So 10 times 4 is 40. 250 times 2 is $5. And so we have 45 equals 45 again. And so our answer is yes. So remember, we're just checking to see if this is true. So it's kind of like we have a little question mark above our equal sign, and we're just testing it. Let's try another one. What about if t is 1 and p is 7? So how about 10 times 1 plus $2.50 times 7? So this is going to be 10. And this is going to be, well, let's see, 6 times 250. If I think about what I had above, 6 times 250 was 15. That's another, it's a 7. So one more $2.50. So that's going to be $17.50. So when I add those together, I do not get 45. So that's not a solution. So sometimes we look at inequalities instead and we say, well, he has no more than $45 to spend. But that's not what they're saying in this. We're saying he spent exactly $45. So this is not going to be a solution. All right, let's see about another one. T equals 2 and p equals 5. So remember we did, let's write our equation here. 10 times our number of t-shirts plus $2.50 for each pair of socks. And we know that he spent 45, so it's equal to $45. So that's what we're using. Helps to kind of have that to look at. So we're going to try a couple more combinations. What if he bought 2 t-shirts and 10 pairs of socks? So 10 times 2 plus 250 times 10. Let's see, does that equal to 45? So again, it's like we have a little question mark above our equal sign. Does this work? So multiply before we add. So we'll multiply here. We'll multiply here. 250 times 10 is just 25. And I can tell this one's going to work as well. So yes, this is another solution. So it's interesting how many different combinations he can buy, right? He could buy less t-shirts and more socks, or more t-shirts and less socks. But there's many different combinations that work to make our $45. But not every combination, because we know that buying just 1 t-shirt and 7 pair of socks didn't work. It wasn't enough money. We know he spent $45. So let's check t equals 2 and p equals 7. So last one we're going to check. So we'll have 10 times 2 plus 250 times 7, and we're going to see if this is equal to 45. And I don't have a good feeling about it because it's almost like the last one, right? Only less sucks. This will be 20. And 250 times 7, what did we get that for that before? I think we got 1750 when we multiplied that out before. So that's definitely not going to equal 45, is it? So that's not a solution. So we can't just pick any old number of t-shirts and pairs of socks. It has to be a set that satisfies this equation. It has to make it true. So remember, in this situation, one constraint is that the combined cost of shirts and socks must equal $45. Solutions to the equation are pairs of t and p values that satisfy this constraint. So I feel like we talked through that when we were doing this. So there's lots of different solutions, but not everything is a solution. This one was not a solution, that last one we looked at. It did not equal $45. We had a couple that didn't work. But there are also lots of different pairs of numbers that did work. So these are our notes for section 2.4. Please make sure you ask questions in class if you have them.